Welcome back to our course on digital accessibility. And we have been discussing several verticals related to emerging technologies over this week. And today we will talk about another emerging technology which can be used as a very important aspect in innovating around new technology innovation, new assistive technologies, or in general just can augment accessibility in day-to-day scenarios, particularly in digital interactions, is something called computer vision models, right? And computer vision models can particularly benefit people who have lack of visual modality, right? It may be low vision, it may be color blindness, it may be uh, visual impairment, it may be blindness itself, permanent, situational, or temporary for that matter. The point being that here in this kind of a technology, what it is capable to do is it can take in um, information from a camera where there is real time visual information, and computer vision, computer processing can try to decipher those real time visual inputs and kind of try to break it down into elements and communicate it to the user itself, and can be kind of a processed augmented version of vision, and that is why it is called computer vision, right? And how it can enable accessibility in different domains is something which we will try to understand in this session. So why it matters is something which I just now also mentioned, that since modern digital interfaces are highly visual, it creates certain barriers for people who have visual impairment or blindness, and many users cannot access visual information, maybe either due to aging or permanent modality impairments, or it may be limitations such as high myopia, or it may be aging related issues, it may be color blindness, it may be all of these other vision related issues, and they cannot access the visual information. So computer vision acts as a visual intermediary between a user who lacks visual control and visual information, and an information system which is highly dependent on vision, for example, right? So it enables independent access to both physical as well as digital world. So let us try to understand what is computer vision, right? And as I said, it's an emerging field of AI. It is enabled by AI. It is called computer vision models. So models are usually ML, machine learning related models that interprets either live video, which is your camera feed, or it can interpret videos, or it can interpret images and extract meaning from that visual data. So all of your face recognition, which now I think your iPhones are opening with face recognition ID, face ID, or facial recognition or number plate recognition from CCTV on highways, all of that comprises falls under computer vision field category. It is used to detect, recognize, and describe visual content. So now I'm sure we have discussed in some of the earlier sessions about automated all text generation, or automated CC, which is closed captioning generation in real time. So that also is sometimes through computer vision models, and where the image is interpreted by a model and then it generates a description. So how a human perceives image is that there is an image, you perceive it, interact with it through your eyes, where the eyes are responsible for sensing or absorbing, taking input the visual um, information, right? And then the brain interprets that visual information and is responsible for understanding the content of the image. So then you are able to kind of uh, put some tags to that image, that okay, there's a bowl, it's a fruit bowl, there are some peaches, there are some oranges, there are some bananas, some lemons, etc. So this is how a human vision system works. A computer vision system, again, there's a camera which is a sensing device. It can be a standalone camera, it can be a camera which is there on your smart glasses, it can be something which is part of your mobile phone also, or whatever camera, right? And then the information is shared to a processing unit. So on a phone, the processing unit is also inbuilt, the phone, or then the information is transferred to a computing system, and then it is able to again generate the similar tags of bowl as well as fruits and other descriptions. So the computer vision models tries to mimic human vision system itself as closely as possible. So computer vision, how it can be leveraged as assistive technology, is also something which is very relevant to our course and our understanding. So computer vision can augment human perception, right? It acts as a visual proxy for users, particularly with blindness or visual impairment. It can provide descriptions, alerts, guidance, etc. Alerts as in if there is some incoming obstacle, if there is somebody, you are going to crash into something. So for navigation related applications, for reading related applications. So now there are applications which you can run on your smart glasses, and you can just look at a printed newspaper, for example, similar to how a person who is able to see reads, and it's a natural form of interaction, and you are able to look at it like how you would read a physical book. And the computer vision models are able to convert those written text into an audio format, and it can communicate the same to you in your earphones. However, it should be thought of that each context or the problem statement has to be thought of when using these models, particularly for accessibility. So it may be related to education, it may be related to navigation, it may be related to obstacle detection, and it may be other features as well. So who are the different users who can benefit from computer vision based accessible applications, right? So one is, which is quite obvious since it's augmenting the visual perception aspect, is users who have blindness or low vision. Then it can also help individuals with cognitive impairment. So, where the user is supposed to interact with certain systems, they are supposed to act in a limited time frame. There are multiple buttons and form fields, etc., but they don't know where to do what. So, if the information is overwhelming in some cases, computer vision models can help simplify it, can help kind of enabling attention diversion or attention um, focus on specific call to action buttons or in a step by step manner. So for example, it is able to there can be applications which are able to, say, kind of turn the rest of the screen dark, and only the step 1 button or step 1 field is highlighted and the rest is dark. So that okay, this is where I have to keep my attention for now. Once it is filled, the next field is highlighted, similar to something like that. Similarly, people who are elderly, they may have diminished cognitive capabilities as well as declined visual capabilities. So for them also, computer vision based accessible applications can be really helpful, either in form of web accessibility, in form of screen based interactions, or in form of navigation applications. There may be multiple solutions which can benefit users who are elderly. And then there can be situational impairments like low light driving in the dark, for example, where you're not able to see where the road divider is, etc. If there are automated systems placed in your car, they themselves can apply automated brakes in case of there's a divider which you are not able to see, or you are distracted and you are unable to kind of divert the car if it is ramming into something. The automated systems can take over and save your life in that sense. So it is also enabling independence in terms of people who are, who may be distracted and may be having situational impairments in some cases. So, what are some core capabilities of computer vision models, and how and what it can really do? So, this can help you develop certain ideas. So, of course, like what we did here is, what we are trying to do is, okay, so what are the different gaps, what are the different challenges that people, different kinds of people may be facing, pertaining primarily to vision based perception and the gaps associated with it. So then you have some idea about the problems or the challenges and gaps, etc. Now, if we try to understand the core capabilities of computer vision models, then we can leverage this technology and try to see where and how this technology can fill those gaps. So, for example, object detection is one of the core capabilities. So, as I mentioned, all your number plate detection in real life scenarios where CCTVs on the highways, etc. There can be obstacle detection related algorithms and applications. Then there can be, of course, text recognition, or which is called OCR. So, of course, one is reading your printed material, or reading a billboard, or reading your printed books, or if you're walking, if there are signages which need to be read. Then also reading your fields which are empty. So, for example, which field is completed, which one is not completed, and all of those things. Then it is also able to do scene understanding, right? So it is able to kind of distill some semantic meaning from the scene. So for example, if there's a beach, there are trees, there is human, there is a horse, there is sky, rock, mallet, water, whatever. So it is able to paint a picture for you. It may not be able to add the context, but it is still able to describe the scene. So it can be in real time scenarios, it can be useful, and it can also be useful in automated alt text generation, in automated scene understanding, where there may be summarizing certain scenes to people who are unable to access the information. Then, of course, as we mentioned earlier, it can be face expression analysis or face recognition. So all of those are part of computer vision models. So how each core capability can be implemented in what kind of scenarios? Let us talk about that. So object detection, how it can be used. So it is able to identify objects in an environment. It can be used in navigation. It can be used in other daily activities. It so example like doors, vehicles, other humans, other person. It is able to detect, or truck. It is able to tell you there's a road sign. So all of this is happening through a computer vision model, and a person who is able to access this information through, say, a smart glass or something, they'll be able to navigate their way through the environment with much more ease and safety. Of course, that is one of the major aspects. So what are the strengths and limitations, particularly in the case of obstacle detection or object detection? So strength is, of course, that there is quick situational awareness, but limitations is that it may miss certain objects, right? It may be useful in unfamiliar environments. It reduces dependency on others, right? These are the some core strengths, and the limitations include that it may miss certain objects. It may not be able to annotate everything in the scene. So if we are even looking here, there is still like this curve which it is missing. So it can still be an obstacle if I'm walking, right? If then there is another signage which is face that side, it is missing that as well. Then and that missing or that real time updation is something also which is dependent on many a time your processing power, your access to cloud in real time, all of those things. It may mislabel items. It may detect item A and label it as item B. So it may really be a pole, but it may identify it as a human or something else. It may be a big truck, but it may identify it as a building, for example. So that can be a dangerous mislabeling, right? So if it identifies a big truck as a wall or a building, wall or a building is essentially a fixed asset, right? It cannot move, but a truck can move. So if you walk in very close to the truck and it starts moving, it can be dangerous. So this part is very important. And then errors increase in cluttered scenes. So if it is like a lot of people or too many signages, too many multicolored kind of scenes, then it becomes very difficult for the models to uh, give real time output with high accuracy. Then comes the next core competency, which is your OCR or text recognition. So text recognition is, as we mentioned, like signboard reading or other like reading material if you want to read. So please do not block the driveway. Thank you. It is able to read that. So it converts printed or digital text into speech, right? So that is what is OCR. And useful for science, documents, and packaging, because if something is delivered to you, you can in real time identify whether it belongs to me or not. Because most of the time the labels on, say, for example, an Amazon package, they're not really accessible or have braille. So an OCR based application can be very useful. It enables access to physical text. And I'm sure you might all have utilized Google Translate application, which is now using OCR technology, and you can just point your camera on any menu card or greeting card or whatever, like a signboard in another language, and it can detect and label it in a different language. Here it is English to English, but real time translation from video or image is also happening very much. So that also enables linguistic uh, access, right? So if, say, for example, I'm traveling to another country, say Japan, and I want to order something from the menu card in a restaurant, it's written in Japanese, I can just point my phone with Google Translate of the with the camera input, and it will in real time tell me what words are written, what are the dish names and items and the prices and everything, right? So that really just removes barrier in real time. Some of the challenges with OCR can be that poor lighting may reduce accuracy, stylized fonts are difficult to read if it is cursive, it is all of those, or calligraphy based, it becomes very difficult. And context or layout may get lost. So if there is a certain sequence that the information is following, if it is converted into audio, it becomes sequential, right? And then there's a particular layout that the visual had in mind, the hierarchy and the size and the color which is utilized to create that hierarchy, all of that is lost. So all the formatting, the layouting is lost in translation in an OCR. The context may also get lost in the OCR. So the third core competency was screen description systems. And what they do is they summarize visual scenes in natural language, right? So it helps users to understand the surroundings, and it may require some contextual interpretation. So if there is a scene, it is able to kind of draw boundaries and tell you, okay, this is a tree, this is a bike, these are some poles, and these are humans, and then these kind of systems are now parallelly used with, say, heat detection, uh, heat sensitive camera as well, in order to identify which one is a live subject and which one is a non-living subject. So live subject means animals, humans, etc., right? Non-living subjects are all your road, bike, poles, all of those. So that those information points can help you add a little bit more context and just not identify living things as poles, for example, right? So that can also give you a little bit more depth of information. But this itself, these models are very difficult to build, and scenes, primarily because scenes are very complex, they can be very ambiguous. There are very important, there may be very important details which add to your semantic understanding as a human, which may be lost in translation, right? So it may be a danger aspect, or it may be some where in the building or where in the campus you are, or something like that, right? So all of the context gets lost in translation, right? Or on the other hand, over description of very mundane, non necessary things can also become very overwhelming for the users. So that is also something which is another limitation of this model. But as I said, so like for example, um, scene recognition along with heat sensitive cameras, along with, say, face recognition, can add a lot of meaning and semantic aspects, or for that matter, OCR, right? So as soon as they in the scene we recognize a signboard, we want to read, okay, what's the text in that signboard? Or if in that scene we are recognizing a human standing in front of us, we would like to know who is that, so that facial recognition comes into picture, right? So all of this in tandem, when they all work in tandem with each other, maybe it becomes even more easier to add the context. So some of the common use cases in which computer vision can be really helpful is, as we mentioned earlier, navigation can be one. So obstacle detection or obstacle avoidance can easily be managed using CV models. Crosswalk or signal recognition, whether the signal is green, whether I can walk across the road right now or not, that is something which it can tell you. It can help in indoor or outdoor wayfinding. So wayfinding means that I want to know, if I'm standing at point A and I want to go to point B, what are the directions I use to reach that other point. So a computer vision model can effectively, theoretically help us do that, but there are a lot of contextual as well as situational parameters which can complicate such problem statements. So we don't want to say that okay, computer vision is the only solution, but it has to work in tandem with a lot of other technologies in order to really solve the wayfinding problem. Other than that, there may be other high stake use cases, right? So street navigation, definitely, because safety is involved. So there is a fast moving vehicle coming, it can warn you. Then reading medication tablets. So if computer vision models can read the tablet labels and tell you that it has to be taken once a day, what is the name of it, which one, which, so you don't take incorrect medicine, or if or not the medicine has expired, for example. So all that label reading, it can be really helpful for, and computer vision applications can do that. Other than that, it can help you in identifying hazards. So if there is a forklift, I mean, for example, something is going to ram into something else, it can warn the systems and stop the car or stop the forklift from ramming into the shelf, for example. Despite the possibilities and the optimistic approach that a computer vision model can offer for a accessible navigation or accessible reading or accessible education problem statement, most of the time we've seen that there are trust and reliability issues, there are accuracy issues because of lower accuracy, there are robustness issues. Robustness means that the same output is not being produced every time because the model behaves in a very probabilistic manner. It predicts, basically, it's not certain, right? And users may over trust the system entirely and then face consequences which are not meant or intertwined in the probabilistic models. Then incorrect output can mislead users, right? So be it wayfinding, be it your label reading, be it um, hazard management, all of those, right? So if you are entirely dependent on computer vision models, there may be cases where the model is missing out on certain hazardous situation, and then there is an accident happening. So entirely trusting these models, at least in their current robustness level or accuracy level, we would not suggest that, but that opens up doors for um, future forward innovation in this domain, future forward research in this domain, right? So this computer vision and AI related machine learning models is one of the major cutting edge research niches currently, which is, very much in demand. So if you are a researcher or a prospective researcher, this can be something you can pursue probably. So, considering that the background processing is not certain, it is not really, it's a probabilistic model, right? So, it is just predicting things. So, then as front end, how we can communicate that information and communicate that uncertainty is also something very interesting for users, or I mean, sorry, for designers to take up as a challenge, right? So the systems should not communicate with confidence. They should communicate the information along with kind of a red flag. So, and avoid definitive language that it will happen or it will not happen. Rather than that, it's always may not. You can try to do this. When unsure, allow users to request clarification, and allow the processing systems to reprocess multiple times to garner a little bit more robust results for the same question. One more important aspect of computer vision systems is bias. And where is this bias coming from? So I'm sure you all might have heard about the term LLM. LLM stands for large language models, and basically what it does is that, say, if my model is trained, so models work primarily on pattern recognition algorithms. So if I have my model is trained on 20 lakh images of different kinds of food, and then in which, I don't know, most of them were apples. Then if I feed it another image, it is likely that it will predict that, okay, whatever food is placed, it is an apple, right? So then that means that there is a bias in the model, in the prediction, because the training data is biased, right? So training data many a times may be unrepresentative. That means that it is not comprising of, say, Indian context, right? So what if our commonly known breakfasts are say a puri or sabji, and then most of the data which is there, the on the which the model is being trained on, is a sandwich, for example, which is breakfast. So as soon as I say, please identify this image, there's breakfast in it, so it may likely predict that, okay, if it is breakfast, it is likely to be a sandwich. It will not even go into other aspects. So that means that the data itself is unrepresentative of different contexts, global aspects, underrepresentation of people with disabilities, underrepresentation of people with varying languages, underrepresentation of people with of different races, etc. Then performance also varies across environments. So again, lighting may be an issue, processing power may be an issue, and all of those aspects may be an issue. So in one of the recent discussions, I think our Prime Minister in his talk mentioned this underrepresentation of data is, if you'll ask GPT, for example, to generate an image of a person writing with a left-handed person writing, it is still likely to generate an image which is right-handed person, because most of the data it is trained on, it is a right hand, that is right-handed, right? So that is the bias that the models have. So, and bias can also increase exclusion rather than bridging the gap and making systems accessible. It can increase a different kind of exclusion, right? So we have to be very careful when using these systems. So, for example, in this image, it is identifying your central character, central food as apple, because most of the food items are apple. This is, say, a disinfectant or something, which is, it is identifying as drink. This is a wallet, but it is, because it is folded and it is looks like that, it is identifying as laptop maybe. Yeah. So all of this are issues. So, and if a banana, if there is like multiple bananas kept like this, it is not able to even identify them as bananas unless it is just one like that. So all of these are biases which are owing to uh, biases in the training data itself. So we have to be very careful when we are utilizing computer vision models, what LLMs it is accessing. Now, particularly pertaining to India, a lot of organizations are developing LLMs which are rooted in Indian, say, languages, the linguistic diversity, image models which are rooted in Indian culture, and all of that. So, I mean, there is a foreseeable future where these kind of models are going to bring in more semantic meaning, more contextual meaning to our applications. Then there may be, apart from this biasness, there may be other privacy or ethical concerns related to computer vision models. So cameras, they capture your personal information, and they also capture bystander data. Bystander data means that when you are not actually actively seeking information, still it is all the time capturing data, it is all the time listening, it is all the time recording. So that is something which has been an ethical concern. So continuous camera use raises privacy issues. Data storage can become a problem because it's continuously recording, continuously processing. Users may feel surveilled at all times. And then consent and awareness, etc., very critical. Then clear control and transparency are required, particularly in this kind of a context. Then there may be on-device versus cloud-based computer vision models. Cloud-based computer vision models are more powerful because they are able to access wider models, wider LLMs, and they are able to compare your image to more use cases in order to identify with higher accuracy. But then there is a privacy risk that your image is going into the cloud and to the internet. On device, there is, that means it is allowing you to download a certain set of model, and it is then only processing using that comparison. It ensures better privacy, but then because of limited resources, the accuracy may be much lower. But the design has to involve trade-offs and look at, okay, in what situations we can go to the cloud, in what situations we have to stay on device. Some of the existing use cases where computer vision models can be very useful. It offers flexibility in use in most of these sectors, so multimodality. It enables use along with your audio and haptics, and it is kind of a replacement for the visual modality, and it can act together with multimodal environments where audio and haptics are also involved, and can be a very good input, kind of an input interaction as well. Multiple modalities, they also reduce reliance on vision. So that is also very useful. And then it improves robustness and usability. So when used along with other means of engagement, other means of interaction like audio and haptics, then computer vision models can be very useful and can be very advantageous in most of the situations. In education, it can be useful in describing diagrams, charts, supporting independent learning, and all of these accessing visual educational content in real time. In everyday life, it can help you in shopping, in product identification, in obstacle detection, in reading menus, signs, signboards, understanding your surrounding, navigation. There are a lot of use cases which computer vision can be really helpful on. But there may be some low resource contexts as well. So there may be limited connectivity in rural areas, or maybe underground floors in malls, for example, or people might be using low end devices which do not have a camera or have a very low resolution camera. Then also the models may not be able to successfully execute the algorithms. There may be battery constraints as well. So design must try to be efficient. Some design principles for accessible computer vision is user control over output. So it should ask the users to kind of personalize how and what way they want to listen to the output. If it is entirely kind of narrating everything, it can be very overwhelming. Then it should be clear and concise description. So this part may require a lot of semantic simplification, which again may be context dependent, which is still something which is we want to say it is still work in progress. And this offers a good opportunity for innovators and researchers to look into something like this as well. Avoid information overload. So this is, of course, as we mentioned, so use it along with your other multimodal aspects, multimodal interaction. Don't convert it entirely into word to word audio. So then that's where the requirement for semantic filtering and semantic simplification comes into picture. And then that is something which needs a lot of work even today. It can support customization. So one thing is, of course, that the user themselves can add certain filters in order to reduce the information overload. So they can say, okay, I am in this kind of an environment. I don't want information about that. I only want information about X. So for example, if you know that you are in a controlled environment, for example, you are attending um, an exhibit in a museum, you know that there cannot be moving vehicles inside the building, but there may be many humans, there may be many obstacles in terms of walking people. So you can say, okay, I don't want information on the chandelier, the wall, the pillar, omit all of that. I am able to detect it with another assistive technology, which is, say, my white cane. So you just tell me about humans coming in my way. So that is customization. And that is also helpful in reducing the semantic load. So, what can be some interesting future directions? So, of course, improved on device models. That is something which requires compression of file sizes and then robustness of LLMs and all of that. Better contextual awareness requires LLMs which are context driven data collection. more inclusive data sets, that this one kind of feeds into this, and that requires more inclusive data sets. And design, trust, and ethics do matter when you are using computer vision models in your solution. So please be careful when you're using this emerging technology. I'm sure you've learned something about it, and please go back and do a little bit of a digging about computer vision models and how it can be utilized in different use cases. And please, you are welcome to discuss those use cases and possible solutions in your discussion forums. Would be happy to answer questions if there are any over email as well. Thank you for joining us today, and I will see you in the next session.